Since our last exam, we've been talking about Earth-like planets and the gas giants, along with the moons and debris of the solar system and solar system formation. Solar system formation right before the last exam. So Earth-like planets and planetary atmospheres, gas giants, moons and debris. Then we moved into talking about the distance ladder, how we find distances to things in the solar system and to the nearby stars using parallax. We then talked about stellar spectra and how we determine the composition and temperature of stars just by looking at them. And then we looked a little bit at measuring the stars in terms of figuring out their luminosities and their temperatures and how that related to the HR diagram. We had a little video about the sun and the solar cycles, and we talked about properties of stars, and I'll talk a little bit more about those in detail here in a second. And then we did an activity on the age of stellar clusters, and then did a little discussion about relativity. So that is the content of the upcoming exam. It seems like a lot, but if you want to kind of put it in perspective, really we're just talking about the solar system, properties of stars, and a little bit of special and general relativity. So I'll talk a little bit about the properties of stars in particular because we spent a lot of time on that, and also a little bit about the distance ladder because that was pretty important to be able to get to the properties of stars. Okay, so I'm not going to let the discussion of Earth-like planets and solar system objects sort of to you, because I think there's some good videos that we put online and some reading you can look at. As far as those things, though, the things that we're really focusing on are surface processes on Earth-like planets, terrestrial rocky planets, and then the difference between different gas giants types that we see in the outer solar system. So whether it's a Neptune type or a Jupiter type, and then also how the giant moons, what their properties are. So you can take a look at that. However, probably more importantly is moving into a discussion of how we figure out where things are in the universe, how far away they are, and then the properties of those things. And that gets into our discussion of stars. So we'll start first with the distance ladder, right? So the distance ladder is something that we talked about right after solar system formation. And the distance ladder was the historical ways that we figured out how far away things were in the solar system and ultimately the distance to the nearby stars. And I want to point out we didn't really know the distance to the nearby stars until the middle of last century, which is pretty amazing considering we started this distance ladder 3,000 years ago. So distance ladder, the properties or the steps in the distance ladder is the first step is we figure out the size of the Earth. And the size of the Earth, we figured that out using shadows at two different latitudes, and then measuring the distance between those two locations and comparing that to the angular separation between those two areas. Once you have the size of the Earth, you can get the size of the Moon by watching the Moon pass through the Earth's shadow. Oh, let's see here. It should say Moon passing through the Earth's shadow, and because you can see the Earth's shadow and you can see how big the Moon looks compared to the Earth's shadow, you can figure out how big the Moon is. And once you know how big the Moon is, you know how far away it is, because you know the physical size, you know how big it looks on the sky, and so you can figure out how far away it is. Once you have the distance to the Moon, you can create a little geometric triangle between the Sun, the Moon, and the Earth. If you wait until this observation happens, this is when the Moon is just a little bit, if you remember your lunar phases, this would be third quarter, this would be full down here, and so this is just a little bit past third quarter, so this is a waning gibbet, or waning crescent moon. And if you wait until that exact configuration where this is a right triangle, then we know this distance right here, right? We know this is a right triangle, and we can measure this angle on the sky by just looking at the angular separation between the Earth or between the Moon and the Sun, and that gives us this distance right here, which is 1 astronomical unit. And they measured that to be 1.5 times 10 to the 11 meters. So this gives you the scale of the solar system, because you also have Kepler's law, which says p squared is equal to r cubed. If this is the distance r, once we know what one astronomical unit is, this relationship gives us the distance to all the known planets in antiquity, because all we have to do is measure how long it takes for them to go around the sun, and then we get how far away they are. So this gets us out to the solar system, and this has, by the way, all been confirmed by radar measurements of the solar system. So in modern times, we can bounce radar signals off of Mercury and figure out how far away it is, and it matches with this whole situation here. Okay, so this gets us out to the solar system. Once you're out to the solar system, though, you've got to get out to the nearby stars, and that's where we use parallax. And you remember you had an activity about parallax where we looked at the fact that if you take two observations of something, so these could be your two eyeballs, or they could be two different points in the Earth's orbit, right? This could be January and this could be July, that if you can take two observations of some relatively nearby object relative to some background stars, then you can see that its position relative to the background stars is going to change. Well, let's put that guy right there. So this is the position of this guy relative to the background stars is going to change. So if I look at it at January, you know, the picture is going to look something like, you know, if we imagine having our thumb out here and January is my right eyeball, then where the object that is in the foreground is going to be over here. And in July, if I have the same star field and I look with my left eyeball, it switches to the right. And the difference between where those two objects appear to show up on the sky is called the parallax angle, right? And the parallax angle, if we draw a triangle here, this parallax angle right here is called P. The distance here is called D, and there's a relationship between the distance and the parallax angle. And they're inversely proportional. And what that means is that as D gets bigger, P gets smaller. And as P gets bigger, D gets smaller. So if you can measure this, if you measure this in arc seconds, then you measure this in parsecs. And parsec is equal to about 3.2 light years. So this measurement is something you can do with very sensitive observations, although you have to have a spaceborne telescope to do it for distant stars, or relatively distant stars. And this distance is something that we can measure pretty easily. So back in the 70s and 80s, we did these measurements. We ended up launching a spaceborne telescope called Hipparcos, which made this measurement out to about 1,000 light years for the nearby stars to high accuracy. And this gave us our first sample of stars where we knew the distance to the stars. So that's the distance ladder, and that's something that is pretty key to astronomy. Once we have the distances to the stars, you can do things like measure their brightness on the sky. And once you have their brightness and their distance, brightness plus distance, those two things together, because we know how far away they are, lets us get something called luminosity. And luminosity is the intrinsic brightness or the intrinsic energy coming out of the star per unit time. So this luminosity is a fundamental property of the star. So as soon as you know the distance, you can tell whether something's fundamentally bright or fundamentally dim. We also can measure temperature of the stars because we can do that by their color. So temperature gives us is determined by the color, right? So that gives us temperature and luminosity, and we wind up with something called the HR diagram. And the HR diagram, which is the Hertzsprung-Russell diagram, named after the two folks who developed this, is a graph of luminosity versus temperature. And this is something we could only do once we knew the distances to the stars, because we had to be able to get their intrinsic luminosity. And we talked about how there's these things called the main sequence stars, right? So this is the main sequence. We had things that evolve off the main sequence into the giant stars, or supergiants. There's giants and supergiants up here. Those things end up evolving to white dwarfs, or neutron stars, or black holes down here. Okay, and we talked about the stellar classification. Stellar classification was O, B, A, F, G, K, M, with M being the redder stars, O being the bluer stars. Temperature went in this direction, where we had hot over here, we had cold over here, and we had dim stars down here, bright stars up here. And the sizes of the stars, the largest, biggest stars are in the upper right-hand corner. The smallest stars are in the lower left-hand corner. So that's the HR diagram, and that's something that allows us to determine the evolution of stars. Once we started talking about the evolution of stars, we looked at what happens to stars as they age, and let me redraw this here. So we have the HR diagram again with luminosity and temperature. We have blue stars up here. Those blue stars are hotter, more massive, right? We have, I don't have a yellow here, so I'm going to say we have our green stars. They're not really green, they're yellow. Green stars right here, which are sort of your middle-aged stars. And then you have your red stars down here, which are your cool stars. And the highest mass stars are blue, and these things are massive, right? So they're really massive. So they have a lot of fuel, but they're also really hot, right? So really hot means they burn through their fuel faster because they have a higher luminosity. And if they have a higher luminosity, even though they have more fuel, they still burn through it faster, and these have a short lifespan. And one of the ways to kind of keep that in mind is that, you know, if you have a giant SUV with a really powerful engine, you have a huge gas tank, but you still can't go very far. So this is the short lifespan. These little middle-aged stars, or so I shouldn't say middle-aged stars, I should say stars that are that can live to middle ages, are sun-like stars here. These are sun-like stars. They have a good amount of fuel, but they're pretty warm still, so they burn pretty quickly. They live about 10 billion years on average. And then these red stars down here are cool. These are the cool stars. They're very small, low mass, but because they're so cool and they burn through their fuel so slowly, these things have very long lifetimes. Let's say long lifetimes. Long lifetimes, like in excess sometimes of 100 billion years. I mean, the universe hasn't even been around that long, but there are stars formed today that could live for up to 100 billion years. So this right here tells us something pretty interesting that we can do with the main sequence. If we can find a cluster of stars that happens to have main sequence stars on them, and we look at the main sequence and we look for what we call the color cutoff, the red cutoff, if we look at a cluster of stars and we don't see any of these guys, and we only see these stars down here, right? If we only see these stars down here, then these stars live to be a certain age, and then all of these have already died. They've already evolved off the main sequence. And so this is something we can use to tell the age of stellar clusters, because if you look at a stellar cluster and you don't see any blue stars, you know it has to be relatively old because those blue stars have already died. Let's see here. Okay. So that's something we can use to tell the age of stellar clusters. Let me draw an HR diagram here again. The other nice thing we can use with stellar clusters is we can use them to tell the distance to that cluster, and by extension any cluster that any object that cluster happens to be in, such as a distant galaxy. So this is a standard HR diagram, and I can draw the main sequence on here. This is the main sequence. And this is something that is, this is a canonical main sequence that happens where we have the solar luminosity of 1L right about here, and this is about 3,000 degrees. Okay. If I were to look at a cluster of stars and measure the relative brightness of these things, right, and the main sequence happened to look something like, like this, where we didn't see some of the main sequence because it was a little bit further away, then I can compare a sun-like star's brightness, because I know the color has to stay the same. This still has to be 3,000 degrees Kelvin. The color has stayed the same, but the brightness is less on the luminosity scale, and the difference between the actual luminosity of a star of that color and the brightness tells you the distance, and that was something that was called the distance modulus. And for the exam, I'm not going to ask you to calculate these things necessarily, but should be able to show you a bunch of star clusters, and you should be able to tell me just by looking at them which one's older, that's the one that's going to have the fewest blue stars, or which one's farther away, that's the one that's going to have the lower brightness. Right? Because even though for the same temperature star, so you can find a sun-like star on the main sequence, and if that has a lower brightness than one of the other clusters of the same, of a star of the same color in another cluster, then you know that one cluster has to be closer than the other. This adds a next step on our distance ladder. So after parallax, we have what's called spectroscopic parallax, spectroscopic parallax. And the parallax is kind of a misnomer here because we're really just using the HR diagram to tell the distance, right? So this is something where we can use the HR diagram and, known properties like, say, the color of a star to get a rough estimate of its distance. So if you find a cluster of stars in a nearby galaxy and you can resolve them and create an HR diagram with those clusters, with the stars in that cluster, then you can determine the distance to that galaxy. And this gets us out pretty far. We can get out to the Andromeda Galaxy, to the Large and Small Magellanic Clouds, which are our companion galaxies. We can even get out with Hubble Space Telescope to some other galaxies in our local group. And so that's something that that is really powerful. Okay, the last thing we talked about with stellar evolution was the fate of high mass and low mass stars. And this is something you'll want to review, go back through your textbook and go back through the smart work to look at what factors are different when we talk about different types of stars. Their ultimate fate is determined by their mass. That's the single most important thing. But the trajectory they go through is slightly different. So I'll make a little chart here. I can put high mass stars on this side, low mass stars on this side, and we'll see if we can see what some of the differences are. High mass, for the sake of argument, are say greater than about 8 solar masses, and low mass would be less than 8 solar masses. Okay, so this is going to be the sun-like stars over here. So you can think about this is what happens to the sun, this is what happens to high mass stars. So let's start off with the thing that's the same. They form and evolve onto the main sequence. Fusing hydrogen into helium. Okay, so that's the same over here. So main sequence, hydrogen into helium fusion. The only difference here is that high mass stars use the CL-NO catalyst cycle that we talked about, and over here they use the proton-proton chain. And that's simply just a matter of which process is more efficient at the specific temperatures inside of the star. So in the case, the result is the same. You're taking 4 hydrogens and turning them into 1 helium and releasing energy. But in the high mass stars, the CNO catalyst cycle is more efficient, so that's what it uses. If it happens to have carbon, nitrogen, and oxygen, the very first stars would not have had those, so they would have had to use proton-proton, but current generation stars do this. These things are short-lived, right? Because they're high mass stars, short-lived. These things are long-lived, relatively, compared to that. These things are going to eventually stop fusing hydrogen into helium, and you'll get shell burning in both cases. Get shell burning over here once they begin to run out of their hydrogen fuel in the core. The difference is, though, is that over here on the low mass stars, you can fuse helium up to oxygen up to carbon, and then after that you pretty much don't have enough mass to compress the star enough to get the temperatures high enough to fuse any further past carbon, right? So this is where you stop, and then once you've run out of oxygen fuel to fuse into carbon, you're going to wind up with a core collapse. And that's going to cause the atmosphere to shed, slough off into the outsides. You're going to wind up getting a white dwarf and a planetary nebula. And they'll just say PNE, planetary nebula. Again, when you're doing this shell burning, this is the red giant phase. And in the case of the sun, that's going to be about the size of the Earth's orbit, so we're pretty much toast at that point. And again, these things go through red giants as well. Okay, now the difference is with the high mass stars is that once you've got the shell burning, this thing goes from helium to oxygen to carbon, blah, 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 all the way up the periodic table to iron, if you're massive enough. And if you're massive enough to get up to iron, that's the hard limit right there, where you can't fuse anymore. There's nothing you can do, and you start to collapse. But because this collapse, this iron, the star is so massive, it's a catastrophic collapse, right? So we get a catastrophic collapse, and that results in something called a supernova. And either a neutron star or a black hole, depending on the mass of the core. Very high mass cores will become black holes. That's a situation where you have the center of the star is so small compared to its mass that not even light can escape. And a neutron star is a star that the electrons merge with the protons to create neutrons, and those neutrons are packed so close together that they can no longer compress. And again, it's just a matter of mass. If you have a neutron star that you can somehow gather enough mass onto it, it will collapse into a black hole. So you can see there's some similarities between the stellar evolution. They both go through the main sequence, they both do shell burning, they both wind up with some remnant, and the atmosphere gets distributed in some way. The differences are that low mass stars are long-lived compared to short-lived high mass stars. The shell burning doesn't go as high on the periodic table compared to high mass stars. And the core collapse for low mass stars does not result in a catastrophic redistribution of material. It is a much more gentle wind that pushes material out. And what you wind up with is a white dwarf instead of a neutron star or a black hole. Okay, so that's the primary differences between low and high mass stellar evolution. And one thing I really want to stress about this is that the stars, when they're formed, they stay on the same point of the main sequence for their entire lifetime until they run out of hydrogen. And so that's why we can look at the main sequence and we can say, oh, that type of star has these properties and will live for this long, because it's going to live at exactly that spot on the main sequence. Okay, what else do we have here? We have, right, so that's our stellar properties. We talked about ages and distances to clusters. So last thing I want to quickly run through is relativity, which was the subject of our last video. And relativity is something that we need to use to understand black holes, and that's why we introduce it here, but it's something that's going to become important for the rest of the course when we talk about the evolution of the universe. So just to remind you, we've got two flavors of relativity. There's special and general. And special relativity has the two main postulates that the laws of physics are the same for everyone. So we have to agree on the outcome of all of the physical events in the universe, because cause and effect is a real thing, and we have to agree. The second thing is that the speed of light is constant, c is constant, for all observers at all times. Okay, so this is always. The speed of light is constant always for everybody. So this velocity additive stuff that we're used to at slow speeds is not true for high speeds. General relativity adds this third piece of information, which is that the inertial mass, so the inertial mass of an object, that's the mass that responds to you pushing on something, is identical to the gravitational mass, which is the mass which is the mass that responds to gravity. Now, this is kind of a subtle point, but it's important. What it really is saying is that no experiment you do can tell the difference between acceleration and gravity. So if I imagine acceleration being, what I mean by acceleration is that if I'm in a rocket ship accelerating up at A, then it feels the same as if I was on the surface of a planet that had gravitational acceleration g. Okay, so A equals G. That you wouldn't be able to do any experiment at all to tell the difference between these two situations, standing on a planet with gravity G or being in a rocket ship accelerating with a acceleration A that's identical to G. And that is something that has been borne out with experiment, because I can do an experiment where I take a laser beam and shine it past a gravitational object, and that laser beam bends. Okay? That's the same thing that would happen as if I was in a rocket ship and I shined a laser beam and the rocket ship moved. It would appear that the laser beam bent. And so that means that light is traveling through space-time in a straight line, but the mass is bending space-time, creating a path that looks curved. Okay, so this is some pretty compelling stuff and pretty difficult stuff to comprehend, because we never move at the speed of light. If we get to a point where your children or your grandchildren are routinely traveling back and forth between the stars at the speed of light, they won't have any problem with this, because it'll just be the way they live. They'll be like, oh yeah, we're traveling at sea. No big deal, I get it. Just like you don't have any trouble throwing a baseball to somebody. But right now it's hard for us to comprehend, because we don't never experience it. So what are the implications of this, right? The implications are we get something known as time dilation, and that's from the experiment that you did with the train. Time dilation. Time dilation just means that moving clocks run slower, right? And that's the only way we can fix this so that both of these things apply at the same time, is that we can't agree on the time. If you're moving at velocity past me, and we measure an event, we will disagree on the duration the event takes to occur. Now, we talked a little bit about space-time diagrams, and I mentioned something about how you can't stop time, and I guess I should be a little bit more clear. I should say you can stop time relative to somebody else. If you're in the room with somebody and you want to measure the time difference between your two clocks, if you're not moving relative to each other, that time difference is zero, right? And a zero time is like stopping time, except you have to say with respect to what. So I can say that no time is elapsing relative to you, because we're both elapsing at the same time. And that's the same thing as saying if we were both standing in the same spot, I could say there's no difference in distance between the two of us, right? Because we're standing in the same location. And all this does is it brings time, the relativity of time, into the things that we're comfortable with the relativity of space. And so I'd write down in here that it also introduces this concept of space-time, which is just saying that before we talked about coordinates x, y, z, you know, up, down, left, right, front, back. Well, time is just like that. And the challenge with that concept is that your perception of time is different. I mean, you perceive time. You can feel the flow of time in your mind that you can't really do with the other coordinates. But Einstein was saying that's just a psychological implication of how your brain interprets space-time. It's not reality. In reality, space and time are identical. Everything's relative, and that's the way it is. Okay, so we have 4 coordinates instead of 3, and I'll point out a little bit later that there are some theories of the universe which suggest there's actually 11 of these, but we'll get to that later. Right now, we'll just deal with the 3 that we experience. Okay, so implications are time dilation, space-time, and the fun thing about this is that means that time travel is actually possible. You do it all the time. You all are living in a time machine that goes forward at a constant rate of 1 second per second. Time travel? No, time travel is possible. And you can do this yourself. If you want to go back in time, just look out into space, because you're looking back in time. It takes time for light to get to you. And so if you go and look at the sun, you see the sun as it was 8 minutes ago. If you look at the moon, that's the way the moon was 1.5 seconds ago. If you look at the Andromeda galaxy, that's the way it was 2 million years ago. You are literally looking back in time. And if you want to go forward in time, we can use time dilation. As long as you travel really, really fast, you can make the time difference between you and the people you left behind as large as you'd like. And so you could take a trip where it only takes an afternoon for you, but you come back and 200,000 years have passed on the Earth. The caveat to this type of time travel is that if you literally wanted to go back in time after you went forward in time, too bad. So if you travel to the future 200,000 years from now, you should just plan on living there because you're stuck. But those are the implications of special and general relativity. Okay, so there we are, and that pretty much covers everything we've got. As far as reviewing the material for the exam, I've listed the activities here for that we did since the last exam. Those are the activities we did. The parallax. Now, stellar spectra, we didn't do the stellar spectra one for credit because there was some specialized equipment in there. But I would go through and look at some of those sections so you can get an idea of what we talked about in the video, and also look at your textbook for that. And then the relativity one, we had two of those. We had the special relativity, and then we had the twin paradox, the time dilation for space travel. The smart work is chapters 6 through 13, and that means assignments 5 through 9, so you should review those for any questions you might have.